Okay, so we're going to talk about informatics today. So I'm actually going to try to combine all the material from the two lectures. So I'm going to go pretty fast, but hopefully we can get through most of it. The last part I'm going to talk about overlaps a little bit with what Tim Hamill talks about. So if we can't get through everything, that's okay. Hopefully Tim will cover it. So these are the lectures. You already had the two lectures from Charles Chu. We're going to talk about Introduction to Informatics, Security, Medical Decision-Making, Databases, and Healthcare Standards. And then Tim on Wednesday will cover LIS, HIS, Medical Vocabularies, and Regulatory Agencies. And then Rick Rogers on Friday will cover selected topics in medical informatics. So the aim is not to have a comprehensive review of informatics or even lab informatics, but just to hit a few major points along the way. So today we're going to talk about these 5 topics. So one definition of informatics that I like is it's the branch of science concerned with the use of computers and communication technology to acquire, store, analyze, communicate, and display medical information and knowledge to facilitate understanding and improve the accuracy, timeliness, and reliability of decision-making. So this doesn't emphasize the underlying technology, but what you do with the underlying technology and how it helps you do something. And in the laboratory, it's how to help manage a lab, how to help lab processes, and in medical informatics in general, it's how to improve the delivery of healthcare. So there's some additional resources that are recommended. So there is a wiki for path informatics, and hopefully it'll keep growing in content and knowledge. So the wiki is actually a really good, easy way to go through a lot of the major topics in a quick and easy way. So you can take a look at that. There's what's called a virtual rotation in pathology informatics. That's divided into modules. You can take modules and learn additional details about different topics in pathology informatics. That's also a very good resource. And then I sent a couple of articles via email, one of which was just talked about medical laboratory informatics, and that's a really good kind of survey of what's important in laboratory informatics, and consequently what they will most likely ask on the rise in boards exams. So we're not even going to cover all the information contained in that article, so I would read the article so you can find out about the important issues. It's a little dated, 5 years ago, but still very current. So what are some of the categories of medical informatics? Different people will categorize it differently, but these are kind of the major topics that are covered in medical informatics. And we'll talk a little bit briefly about each one. So under imaging informatics, it's all of medical imaging, image analysis, process, storage, retrieval, signal conditioning, compression, and enhancement is important when you're trying to send a large quantity of data downstream. So that's important in pathology because we're getting into the era of pulse-light imaging and how to retrieve that information, which is an order of magnitude greater than the information that a radiologist will need. So there's a lot more data on a slide than there is in an MRI or CT series. So it becomes important, how do you best send that data downstream? And high-performance communication goes along with that. If you have, a lot of this data, the bigger pipe you can send it down through, the better or the faster it'll get there. So all of these are concerns in information or in imaging informatics. And then we have biomedical computing. There's a close relationship between biomedical computing and bioinformatics. But biomedical computing is concerned with computational biology, chemistry, and medicine. A lot of computer graphics, high-performance computing underneath this as well. There's a lot of work in modeling and simulation, molecular design, and systems simulation. So by systems, more often biological systems. How do you model biological systems so that you can do drug discovery, drug development, things like that. And then under decision science and engineering, you have the clinical informatics, and here's where you have expert systems and decision support. We'll talk about these two things in a little bit of detail. Health services research, outcomes research and analysis. There's a big emphasis right now on outcomes research and analysis because it looks like the healthcare industry is going to is moving in a direction where it's going to reimburse for quality of care. And in order to gauge quality, you have to determine, what kind of outcomes you have, whether they're good outcomes, bad outcomes, et cetera. So there's a lot of effort going into there so that you can judge, the quality of care at a given hospital and be able to compare different hospitals in terms of quality of care. Policy and cost-effective analysis, quality assessment, and improvement fall under decision science and engineering. And then bioinformatics, you got a really good introduction from Charles Chu, but biotechnology, gene mapping, genome structure, sequence databases, macromolecular structure, function and how that relates to sequence. Still, the holy grail is to go from primary sequence and derive function from that. We're still not at that stage yet, but getting closer and closer to there. And the big challenge in bioinformatics is information representation. How do you analyze and how do you present the data from, let's say, array studies or from whole genome sequencing, and how do you mine that information for further diagnostic information. So all of that comes under the rubric of bioinformatics. And then knowledge management, a heavy emphasis here is human-computer interactions. How do you maximize the use of information systems for the end user? Here at UCSF, just went live for inpatients with our new medical record software, Epic. We call it Apex here. I can tell you there's a lot of failure right now of human-computer interactions in the initial ramp-up. So how do you design systems so that they're easy to use and don't place the burden of additional time on the end users? Also interested in distance learning practice and research. Distance learning, we're getting into the era in pathology of being able to view slides at a distance, right? So instead of having to be at a microscope with whole slide imaging, you can be at home if your pipe is big enough, or somewhere else in the hospital system. So that's really important for education. So you have computer-aided education as well as knowledge acquisition, retrieval, and representation. And again, how do you best present the information to the user so it's easily digestible, understandable, and they can then make medical decisions based on it, or make the optimal medical decisions based on that. And then database science and engineering. This underlies a lot of what we do in laboratory medicine because if you look at, just in terms of volume of discrete information, the lab produces, the greatest volume of discrete information in the electronic health record. So our annual test volume at UCSF is on the order of about 5.5 million tests per year. That's a lot of data that gets pumped into the electronic health record. So you have to have a way of storing that, retrieving it, and sending it down to the downstream systems. And that's getting more and more difficult because traditional lab information systems are used to dealing with either short textual information or discrete numerical information, but array data is none of those. Whole genome sequencing is none of those. So right now, LIS lab information system vendors are struggling how to update their information systems to deal with all of this information. You have to deal with heterogeneous databases. How do you represent healthcare concepts in a database? We'll talk a little bit about that. The unified language systems and thesauri are important, and we'll talk about that at the end. And then just healthcare records in general. How do you store all this information? And even more important, as we're heading into an era of increased push towards electronic health records, how do you share this information between hospital systems? Right now, it's very difficult to share that information electronically. But the goal is to seamlessly be able to send all the information for a patient somewhere else and have it immediately available. So that was a very, very, very fast, brief introduction to medical informatics. So one of the big topics in medical informatics is security. Oops, and this is the wrong slide because we're not going to talk about all of this stuff. But that's okay. So security. There's a lot of different things that come into play when you think of security. One of them is physical security. How do you physically secure your data? And a lot of that is how do you physically secure a server? So what you do is you put it in a data closet or a data center, and you have restricted access. Typically, data centers will have card access so that you can track who goes in and who goes out in case there's any kind of mishap. Along with physical security is disaster recovery planning as well as backup planning. So you have to make sure that data is always accessible, even if you have a server that goes down, if you have the internet that goes down, etc. And then firewalls play an important part in securing your organization. So firewalls can either be software or hardware or a combination thereof that secure your network from the outside world.
Do we have remote servers that we store our backup information at?
Yeah, it's in San Diego. So UC San Diego. So UC San Diego has a large-scale data center. And we've contracted with UC San Diego to, put servers there, and they manage the servers, they take care of the servers, they, change backup tapes, etc. So we have a lot of our systems duplicated down there. So if, our data center goes down, hopefully, it's like an earthquake or something. Then hopefully San Diego's not affected, and someone down there can go in and fire up the systems, and potentially we could send someone down to San Diego to help out and stuff. But yes, we have disaster recovery in a data center in San Diego. It used to be in Sacramento, but Sacramento is also along the same kind of fault lines that we are, so that wasn't kind of too smart of an idea.
Code blue, long 1337, code blue, 1337 long, 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 code blue, 1337 long.
And it's interesting because back in like the 70s, 80s, 90s, mainframes were very much in vogue. Just large machines that took care of most of the computer functioning that was needed in an organization. And the world gradually moved away from mainframes to more servers dedicated to single tasks. And IBM used to be really huge in mainframes, and they had to readjust their business model to deal with mainframes going away. And now we're moving back towards that environment because of a new concept in computing, and that's something called virtualization. So you can still have kind of single-purpose servers, but if you have, for example, a mainframe-type computer, you can do what's called virtualize. You can encapsulate that server operating system into a virtual environment that can run on a mainframe, and a mainframe can run lots and lots of these virtual environments. So why would the world be moving more towards that? Because if you can virtualize a server, that means you can run it on lots of different hardware and not have to worry about individual servers going down. And the more of these that you can virtualize into one machine, you reduce your power requirements, you reduce your kind of network port requirements. So it makes it a lot easier to consolidate lots of different things into a data center, and thus increase your security, because if you have all these servers all over the place in your organization, that's a big security risk. It's not all centralized. You have to have power, redundant power. You have to have redundant network. So you can achieve a lot of efficiencies by moving towards virtualization, and that makes it a lot easier for disaster recovery, because if you can virtualize in your own data center, that means you can virtualize in a different data center. And instead of having duplicate hardware, all you have to do is just synchronize the virtual server file across to a different data center, and you have your disaster recovery in place. So, and it makes it a lot easier to redeploy a server or replace a server, because if hardware fails, then you have to get a new server, you have to reinstall the operating system or restore from backup. But if your backup is just a file and you can just restore a file and there you have your server again, it makes it a lot easier. So, so the world is moving towards virtualization to increase security. So now we went away from mainframes, now we're heading back towards mainframes or mainframe-type computing environment. Encryption is very important. And encryption is just a way of encoding messages so that anyone intercepting the message can't read it, and only the intended recipients can decipher it. And this is important in the era of HIPAA, because one of the provisions of HIPAA is a security provision, and one of the provisions is that if you use the internet to transport patient health information or protected health information, it has to be encrypted. So this is an important part of any type of security. And actually, the Achilles heel of security is the user itself, himself or herself. And there's four main concepts that come under the rubric of user security. One is authorization, authentication, access, and audit trail. So authentication is kind of proving that the user is who they say they are. Authorization is, okay, once you've proven that they are who they say they are, do they have access to your system, and what type of access do they have, so that user can't do something that they're not supposed to do or can't access data that they're not supposed to access. And that's goes under access as well. And then audit trail. In the era of HIPAA, you need an audit trail, because you need to know who modified the information in what way, and also who looked at the data. Because another provision of HIPAA is that patients have the right to request an audit trail of who looked at their protected health information. So you have to be able to provide that. It also helps if you suspect a breach, or you suspect employees doing something that they're not supposed to. And one of those things that employees can do that they're not supposed to do is look at patient information that for patients that they aren't taken care of. And that's actually happened. In UCLA, they had a case of a famous celebrity who was admitted to the hospital, and lots and lots of people took a look at the medical record, and several people got fired because of that. So that's important. And we actually had a situation where a celebrity was here at UCSF, and they took a look at access, and they kind of called some people to state why they accessed the data, and one of them was one of our residents. But it turned out that this celebrity had suspected von Willebrand's disease, so that's why the resident took a look at it and was suggesting testing. So that's what the resident said, and they were like, okay, fine.
Whatever that is, sure.
But usually celebrities, when they're admitted, they go under a pseudonym. So the resident didn't even know it was a celebrity.
They had issues like that at the General when that
Giants
fan,
fan?
that Giants fan
Oh, okay.
was transferred there. Right?
Yeah. So be careful if friends, ask you, oh, can you take a look at my record and, for me. So I would think twice about that. Let's see. So under security, there's some terms to define. Confidentiality is ensuring that only authorized persons can access data. Integrity means ensuring that information is modified only in expected ways. And availability, ensuring that information is not erased or made inaccessible. And the difference between security and privacy is that privacy is the right of a person to protect their personal life from the outside world. And HIPAA has both security as well as privacy components to that federal legislation. Other things involved in physical security, as I mentioned, securing the data. You want to lock the server. You want to have off-site storage, for example, backups, so that if you have all the backups in your primary organization and you don't have anything off-site, if something knocks down your server or your data center, chances are it could also knock off your backups. So you want to have data in remote sites, and of course you want to have a backup as well as disaster recovery plan in place. There's another way, so that goes under physically securing the data. And then you also want to secure access, so typically you have redundant servers, so that if one server goes down, another server's still up and running. And then there's ways of securing data, and one of them is you have, instead of a single hard drive, you have multiple hard drives where you write the data to multiple hard drives. So if one hard drive fails, you can just replace it, and your business continuity keeps going. And it's also a way of increasing speed because writing to disk turns out to be one of the slowest processes in a computer. So if instead of writing all the data to one disk, if you can divide half the data to one disk and half the data to another disk, you can speed up by a factor of 2 the speed of both writing and reading from the software. So RAID can encompass both. You can do what's called mirroring, write the same data to multiple disks, as well as spanning or striping, meaning divide the writes and reads to different disks so that you get an increase in speed. And then firewalls, of course, is a way of protecting your internal network from the external internet. So it will block unauthorized access. And typically, what you do is you poke holes through the firewall, meaning there's certain ways to get through the firewall. One way is using a VPN, virtual private network, which establishes a secure, encrypted connection between your computer and the corporate network. And the other way to poke a hole is to use web technologies with encryption so that someone can authenticate against a web server and then be allowed access to resources within the network. So UCSF uses both. You can VPN in, or you can go to websites and be able to access the medical record at UCSF. But this is an important component of security.
So right now they have that UCare Connect system.
Mm-hmm.
Is that going to go away since UCare is gone?
Or? Yeah, now it's just
there's a new website.
Connect.
Oh, there's a new website.
Yeah.
At UCSF Medical Center.
I think it's just connect.ucsfmedicalcenter.org now.
Oh, okay. And then you just put in the same login information.
Yeah.
Okay.
And it dumps you into Apex instead of
UCare.
UCare. Yeah, because UCare is no longer here. And if they were smart, hopefully they redirected UCare Connect to just Connect.
Yeah.
So that's probably what they did. I'd be surprised if they didn't do something like that.
They didn't.
They didn't?
Okay. It's just Connect now.
I think it's just Connect, yeah. Except if you're on, I think if you're on the Mac, I tried this. You have to have the Citrix software loaded on your computer in order for it to work.
Same for the
PC? Okay, yeah.
download some.
Yeah.
It prompts you to download it.
Okay. So,
pretty seamless.
But if you have the software, then you go to the website and then it establishes an encrypted tunnel so you can get to the information. So, and then under encryption, there's you can have a simple translation table, which is easy to crack. I mean, that's kind of what they used in the old days. If you have a computer, then you can do all kinds of stuff. You can rotate words, bytes within the data stream, use multiple and variable duration of the rotation to encrypt the data. And you want to make it complex enough that you have a reasonable assurance that someone else with a computer won't be able to break that encryption methodology. The kind of newer encryption technology is what's called key-based encryption. And this basically arose from the need to be able to send encrypted data but not have to contact the other person to decide, okay, what encryption methodology are we going to use? As you can imagine, that can be difficult to be able to send encrypted information. What web browsers will do, they basically do this behind the scenes because when you connect to a secure web browser, via that connection, you kind of negotiate the encryption keys that will be used for that particular session. But if let's say I want to send a file that has sensitive information to Tab, I either need to use secure email, or if I use key-based encryption, I would be able to encrypt that, send it to Tab, and only have Tab be able to encrypt it. So how does that come about? This is based on the ability to be able to specify a key or a password of some kind and have the encryption method alter itself, such as the key or password produces a different encrypted output, which requires a unique key or password to decrypt. So when you use symmetrical systems, both the encrypt and decrypt use the same key. When you use asymmetrical system, the encryption and decryption keys are different. And that's where the beauty of the key-based encryption comes in. Because what you can do is you can set up on a one-time basis your decryption key, which is called the private key, and your encryption key, which is called the public key, so that you can distribute your public key to the world so that they can encrypt information, and only the person who has the decryption key would be able to read that information. So if Tab keeps his decryption key private and doesn't give that to anyone else and just gives everyone the public key, then only he can decrypt anything that's encrypted with the public key. So how can you do that with any reasonable assurance? Well, if you think back to basic math, most functions are reversible, right? Meaning if you can get mathematically from A to B, there's usually inverse functions that can get you from B to A, right? Except there's a couple of cases where you can't do that. If you get to a case where the reverse involves dividing by 0 or taking the square root or something, it's not easily reversible. So if you have a process that's not reversible, then that's how you can end up with public and private keys, because your public key can go from A to B, but you can't go back from B to A unless you have the private key. And it's actually based on prime numbers. So if you take an arbitrarily huge number, it's really hard to figure out what multiples of prime numbers will get you a huge number. You can take very large prime numbers and multiply them together to get a huge number. And if you're just given that huge number, it can take a computer a long time to figure out, which are the prime numbers that multiplied will get you that number. It turned out to be a complex mathematical function, which basically is just a brute force methodology. You just start with prime numbers and start multiplying them out. And if you start off with very large prime numbers and multiply those, then it's very hard to do the reverse. And so the keys in the key-based encryption are based on large prime numbers. So it's pretty safe. As long as you use at least 128-bit encryption, you can be reasonably sure that no one's going to be able to decrypt it, at least today. Maybe in the future, but not today. So even before HIPAA came about, HIPAA, the Healthcare Finance Administration, allowed transmission over the Internet, but specified that you had to have encryption technology, and it specified minimum levels of encryption. So these are all different encryption methodologies, and it defined the minimum encryption level. So this minimum encryption level ensures that if you use this, no one can reasonably crack your encryption unless they get extremely lucky. So why do I mention 128-bit encryption? Because with 56-bit encryption, the Electronic Frontier Foundation back in 1998 just used off-the-shelf computer components at a cost of about $40,000 to $50,000, but it took them 3 days to crack it. Nowadays, you can probably do it on a Mac laptop in less than a day. So don't use 56-bit encryption. 128-bit encryption is reasonably secure, and actually nowadays you can get 256-bit encryption pretty easily. So
how do you get 56-bit? It's an odd number.
It is. You can get arbitrary level encryption in terms of bits. It just means what power of 2 are you using?
Isn't it just more natural to use 64?
It's more natural to use 64, yeah.
Okay.
Because it's an even multiple, right? To get 56-bit encryption, you have to have probably like 32-bit encryption, and then on top of that, another layer of, let's see, 32, 20, 24-bit encryption on top of that. So,
okay,
it's an odd number. 128-bit is an even kind of power of 2, as well as 256-bit. But back when, in 1998, when computers weren't that fast, 128-bit wasn't easily achievable, and 32-bit was too easy to crack. So it was more of a compromise. Okay, so HIPAA, everyone knows what HIPAA is. Federal legislation that encompasses security as well as privacy components. And it came about in 1996, although you had different timelines for implementing the security provisions as well as the privacy provisions. The privacy provisions came first, and then the security provisions came second. And it applies to all covered entities, hospitals, physicians, other providers, and health plans. So it provides rights to patients, and that's a privacy rule, right to request access to their own health and research records, right to request amendment or addendum of information, and a right to receive an accounting of disclosures of their information, and that's where the audit trail comes in. You have to be able to provide that. And at the time HIPAA came in, California had different laws that had already been in place. But HIPAA supplemented what was already under California law with requirements that organization appoint a privacy officer and a committee, which we have both. Deborah Yano Fong is our privacy officer. Establish administrative, technical, physical safeguards for protected health information, and we have all of those. Respond to patient requests to learn who has access to their information. We had to build a website where disclosures are all logged so that if a patient requests an audit trail, they can just go through all the disclosures. And provide patients with a notice of privacy practice to explain how the covered entity will handle information. And if usually anytime you go to a provider, you'll get a notice of privacy practice from that provider. Providers must make good faith effort to obtain written acknowledgement of the patient's receipt of the notice of privacy practice, and access to PHI by faculty, staff, students, trainees is based on the general principles of need to know and minimum necessary. Basically, access only the patient information needed to get your job done. There's potential consequences of breaking the law, can impose penalties and fines for breaches of privacy, and they can impose fines per incident. So, if you have lots of employees accessing, the same celebrities' information, it's not just a single fine. Each instance of access can result in a fine, and the fines are usually in the order of $17,000, so it can add up pretty quick. And then there's others. You can be fined $250,000, imprisoned for 10 years, go into lawsuits, etc. The administration simplification rules included 4 main provisions: uniform electronic transaction standards for healthcare data, privacy and confidentiality provisions, security procedures to protect electronic information, and unique health identifiers for providers, employer plans, and individuals to be used in connection with the uniform electronic transaction standards. We don't have unique health identifiers. We don't have national unique health identifiers for individuals yet. They've been proposed, but privacy concerns have kind of squashed any efforts to go to national unique identifiers for individuals. For physicians, there was very little resistance, so physicians have national unique health identifiers. It's called the MPI number, National Provider Identification. So when did they take into effect the privacy rule? April 14th of 2003. Uniform transaction standards, also around the same time, April 16th, 2003. Security rule was April 21, 2005. There was recognition that it would take more time to implement the security provisions than the privacy rule. So is that it for federal legislation? Not quite. We had the American Recovery and Reinvestment Act of 2009, also called ARRA, and one of the provisions of the ARRA is the HITECH Act, the Health Information Technology for Economic and Clinical Health Act, or just called the HITECH Act or the Act. So what does it do? It provides incentive related to healthcare information technology in general. And the push is to get everyone to use EHRs so that we can get to a point where we can have interoperability of EHRs and we can have information stored electronically. A big buzzword under the HITECH Act is this meaningful use. There's some provisions of high tech for meaningful use, meaning that it's not just enough to install an EHR. You have to use it, and you have to use it in certain ways, and you have to ensure that a certain percentage of the physicians are using it, et cetera. So that's all encompassed under meaningful use. It's actually one of the big topics in healthcare right now, and which is why, along with that email, I distributed an article on meaningful use. So you should read that. I don't have time to go into it in detail, but it is a hugely important topic because it translates into money for your organization. Okay, I got to speed up. Computer-assisted medical decision-making. So why actually go into this at all? It doesn't impact pathology that much, but unfortunately it has appeared on boards. So at least the boards, the American Board of Pathology, thought it was somewhat important. So computer-assisted medical decision can fall under various categories, but there's two big categories. One is called expert systems, and that's contrasted with what are called data-based approaches. So under data-based approaches, you can have several different types, but neural networks are the most common ones that are used. So on one side you have expert systems, on the other side you have data-based approaches, of which neural networks are the most prevalent in use. So expert systems have been around since the 80s. There's three examples: Reconsider, De-Explain. This one is available on the internet. You can actually go look for it and see what it does. And Iliad. And they all basically are aids for differential diagnosis. So you give signs and symptoms and spits out a differential diagnosis. It's helpful for thinking about some uncommon diseases that can be part of the differential diagnosis. But traditionally, they've been hard to use because they required a physician to go to a computer and enter a lot of information. But now that we have electronic health records, and maybe it's getting easier and easier to incorporate expert systems into the electronic health record so that they're easier to use. So some of the drawbacks of traditional computer approaches was that strict algorithmic approaches were unsuccessful because complete models that describe biological system functioning were not known. You can try to develop a model, a computer model, but the computer models tended not to be very complete or very accurate, leading to inaccurate kind of differential diagnosis or inaccurate output of your data. So the lack of algorithms led to the development of pattern recognition or database approaches to address the classification problem. And as I said, one of the earliest ones were neural networks, also one of the most prevalent ones. The motivating factor behind neural networks was the modeling the structure of the biological nervous system. They're also referred to as artificial neural networks, or ANNs. So, just kind of go over the important parts of neuron, right? So neurons have dendrites, and they have an axon, right? So what do the dendrites do?
Gather up information.
Gather up information, right, from lots of different neurons. And what does the axon do?
It sends out kind of the output from the neuron, like what the neuron wants.
Right. It can send it out, right? So a signal can come in from the dendrites and potentially go down to the axon, right? But there's a threshold, right, that you have to exceed in order for the signal to become propagated. So you can get something coming in, a signal coming in, but it won't be propagated unless the threshold is reached. And if the threshold is reached, then the signal is propagated, right? And this is basically the model of neural networks. So you have what are called nodes, and you have input from, lots of nodes going into a particular node. It can fire off and to other nodes depending on the threshold. So it allows you to gather disparate and information into one place and decide, am I going to do something with that information? So why is that important? There's a few steps that are involved in neural networks. So you can have supervised learning, where you take data of known classification, and you use that to determine important parameters that contribute to the correct decision. Or you can have unsupervised learning, where you have data of unknown classification that are used, and your objective is to find patterns in the data that allow the data to be grouped or clustered according to similar characteristics. Most of the time you use supervised learning. So the first step is problem definition. So, what problem are you trying to solve? So one problem may be, diagnosis of MI. So someone presents with certain signs and symptoms, and you want to know, does this patient have an MI or not? Because you want to know, can I send them back out from the ED, or do I have to admit this patient? So then you go to feature extraction. So you try to think of, well, what features, what signs and symptoms are important to determine whether someone has an MI. So what are some of the things that would be important? Symptomatically, or lab values, or anything. Right. Blood pressure.
Sure.
Pulse. History. Pain.
Yep. Radiation.
Radiation. So all those things, right? So you might think all those things are important. EKG, right? Changes on EKG. So that would be a part of your feature extraction. You might want to use all those as inputs to determine does someone have an MI. And then you have the training. So once you get all the features that you want to extract, or the variables that you want to input into your neural network, then you train. Then you test. So you have training cases, you have testing cases, and then you have new cases that you then try to classify. So this is important, the training versus testing, because it's possible to overtrain, meaning that your neural network works great, fantastic on your test cases, but once you try to generalize it, it breaks apart. So you need the training, testing, in order to make sure that you haven't overtrained to the cases. So what is a neural network? You have these nodes that you define, and you can have as many layers as you want to increase the complexity and to increase the data that you gathered. So each one of these nodes basically represents a computer algorithm, right? You take an input, you transform it via a computer algorithm, and that gives you an output that you can send to additional nodes downstream. So you have an input layer where each of these is one of the variables that we discussed. And you assign computer algorithms to each one of these nodes. And then your variables will come in. You may or may not propagate a signal to another node that will take lots of signals, and again, in turn, may or may not propagate a signal down to any downstream nodes. And then at the end, you have the output layer where that will give you an answer. And since these are all mathematical transformations, usually the answer is going to be yes or no. And you define a threshold for your output layer to get yes or no. So as you train it, you make tweaks to each one of these nodes or each one of the algorithms until it gives you the kind of desired answer. So it's basically just a mathematical transformation of all these variables. But you don't need to know anything about what an MI is in order to get an answer. You just need to know what's important in diagnosing the MI. And all you need are the variables once you train your neural network. So once you have it, it's very easy to perform later on. So the advantage is it doesn't require expert knowledge and will not become obsolete when the rest of it changed colors when the knowledge in the field advances. Disadvantage, it's a black box. You get an answer, right? Yes or no, am I? You have no idea what kind of reasoning went into saying yes or no. You just know that you have an answer. Physicians hate black boxes. They like to know how you arrived at an answer. like I said, you can overtrain, but that's why you want to have test cases. And then this is kind of an esoteric topic: local minima when you're determining the weight assigned to each one of the nodes. That just means you can get stuck and not get the right answer. You can get stuck at the easiest answer and not the most correct answer. And it requires a set amount of cases, 10 per variable that you're looking at. If you're looking at 10 variables, you require 100 cases. So it's really hard to write neural networks for rare diseases. You would need to have all those cases set up. So expert systems are kind of the opposite. You have to have expert knowledge because most of the expert systems are based on production rules. Things like if condition A and condition B and condition C exist, then something. So you really have to have an expert who can kind of regurgitate how they go about diagnosing a case or approaching a case. And they have to regurgitate it in a way that you can then model it as a computer program. And then the conditions and rules can have several components. The rules can have as many rules as you need, as many conditions tested as you need. So this is actually an excerpt of one of them. If the site of the culture is one of the sites that's normally sterile and the port of entry of the organism is the same site as the prior organism with the same identity as its current organism, then there's further suggested evidence that each of them is a prior organism with the same identity as the current organism. So expert systems, you have all these if, then, and, else statements strung together. Advantages, you can get a detailed account of which production rules fired. Physicians love this. You don't need patient cases to build a database of knowledge, so you can look at rare diseases. Advantage rules written by experts, and it's a flexible model. The disadvantage, you need to extract all that expert knowledge. Limited to clearly defined problems. Consistency is difficult to maintain. Redundancy difficult to avoid. Rules can't be easily derived from actual data by a machine. Development time is consuming and expensive. And if the knowledge in the field advances, your expert system can be obsolete. So those are the two different types. So we're going to cover databases in a couple of minutes. You can have different elements of a database system: the hardware, the software, users, and database administrator, and most importantly, the data itself. They're typically divided into analytic and operational. The reason being, one is basically read-only database for reports and things like that. The other is where you do all your transactions. The reason to divide them is if you need to do a big query on the database, you don't want to slow down the users that are trying to use the database to conduct clinical information. And in fact, when AP, when they first implemented COPATH, the analytical and operational was on the same server. So whenever they would try to run a big report, it would slow things way down for people trying to enter their cases in there. So they finally had to separate these two servers and run reports on a different server. And even now, there's only defined times when they run reports. So you'll see this kind of dichotomy when you're trying to access information from a database. And a lot of times these are called data warehouses. So that's basically just read-only for reports. There's several different types of databases. I put in italics the most important ones. Hierarchical, relational, and the NoSQL is the newest type of database. So flat file databases are simple, easy to create. Single computer file is your database. Typically, these are like Excel files where you can have columns of information, and you can list them all in a file. The problem is that they're inefficient. You can make them a little bit more efficient if you tie an index to them, but they're still very inefficient. You can have data redundancy, poor data control. Can't easily manipulate the data, and because of all this, you can have cryptic workflows. Hierarchical databases were a huge step up, and you define hierarchically arranged data. So, one of the most common hierarchies in biology is just categorization, right? So you have the kingdom, phylum, class, order, order.
King's plate.
So Feingold says. Anyway, so you can hierarchically store data. The problem with hierarchy is that a child can have one parent, but parents can also have multiple children, and that's not modeled very well in this. You can have, for example, courses with students, and then finally students have grades. But a student can take multiple courses, and in a hierarchy, it's difficult to tie the same student to multiple courses. It looks something like this, where you have the same student kind of replicated among different things. The problem is if you change information here, it might not change it there. So although hierarchies are very easy to model, access is very fast, it has this one problem. Network databases solve part of the problem, but they were difficult to maintain. Relational database solved it permanently. You can have many-to-many relationship with these. You have CODS rules, that rules for relational databases. Here's an example. Basically what you have is an ID that is replicated among tables, so that you can go from the admission table or the secondary discharge diagnosis table, tie it to a particular admission tied to a specific patient from the patient ID. So from these relationships, you can model the data as much as you want. And it uses SQL language for the database language. And the no SQL databases came up because relational databases are difficult to cope with a large amount of data. Google, Amazon, Facebook all have a large amount of data. It doesn't use SQL as a query language. It doesn't give the full guarantees that a relational database gives. And it has a distributed fault-tolerant architecture, which is fine because if your post to Facebook doesn't make it to all the replicated databases initially, that's okay. It just means that maybe someone looking for your post might not be able to see it right away, but if they see it later, that's fine. That happens with your bank, though. If it fails to process your payroll check before your debits, then that's a big, huge problem. So different things for different things. So I'll stop here and let you find out about healthcare standards from Tim or from the PowerPoint. Sorry for going over.